since molarity is how concentrated solution is in terms of moles of solute to liter of solution it's swimming around in, those are like 3 variables. And I don't know, you've had algebra, probably. So if that's what we call one equation, you can have one unknown, and as long as you have the other 2, you can solve for that unknown. So it looks like this, as long as you know 2 of those things, so what those quantities are. If you know the molarity and the volume, you can come up with moles. If you know the moles and the volume, you can come up with molarity. Oh, what's the last one? If you know the moles and molarity, you can come up with volume. So just need to know two of those 3 quantities, and you can knock out the third. So in this sort of problem we're going to do, we make use of that. So I think what I'm going to do is write this up on the board. These are a type of reaction or a type of problem that involve actually both stoichiometry and solution concentration. And the reason I'm going to put up on the board is I kind of want to refer to it as we work the problem. H2SO4, that's a strong acid, that's sulfuric acid, and it is going to react, 1 mole of that is going to react with 2 moles of NaOH, is sodium hydroxide, and this is a nice acid-base reaction, which works well for this sort of problem. And it's going to form sodium sulfate, Na2SO4, 1 mole of that, and it's also going to kick off 2 moles of water. And so what I like to do with this sort of problem is I take the information that's given and I kind of put it under the species it's talking about. So it says what volume of, the first thing I know is 0.235 molar NaOH. So I find my NaOH and I literally write 0.235 m. And one of the things we need to remember is what that m means, like you saw in the previous slide. That means for this solution, there's 0.235 moles of NaOH in 1 liter of solution. The problem goes on to say, oh, and with regard to the NaOH, it says what volume. So I'll put question mark volume. And then it switches gears. Is needed to react with, and notice I have a 35.0 milliliters and a 0.108 molar, but that's about my H2SO4, so I put under my H2SO4. So 0.108 molar, that's how concentrated it is, and the volume of H2SO4 is 35.0 milliliters. And the reason I like to write it underneath what it's talking about is then you can look back and you're like, oh, well, I know most about my H2SO4. So here in a minute, when we work the problem, we're going to see that we can use the molarity and the volume of this to get to moles of that. Moles of H2SO4. Then we can go from moles of H2SO4, skip over to moles of NaOH using the stoichiometric ratio that we've done before with our other sort of calculations. So stoich ratio. And once I have moles of NaOH, now I can use moles of NaOH, and I'll just go ahead and say molarity to knock out volume. So it's kind of like a circular sort of thing. So there's kind of 3 different problems, and I usually kind of keep it separate as 3 problems for this sort of problem. So this says we can use for the H2SO4, we can use the molarity and the volume to get to moles. We can use stoichiometry to get from moles of H2SO4 to moles of NaOH. Once we have moles of NaOH, we can use molarity to knock out volume. So what these sort of problems have in common is that you have enough information about something to get to moles, and then you then you just kind of let it roll from there. So the first thing is we need to get to moles of H2SO4 from our molarity and our volume. So there's a few ways to work this, but I'm going to make 35.0 milliliters as my first term. And then I'm going to use molarity as a conversion factor. Keep in mind that what that 0.108 m means. means 0.108 moles of H2SO4 per 1 liter of solution. So my point was going to be that molarity is moles per liter, and I can't do it with milliliters. So I think we've done this before. I need to convert my milliliters into liters. So if I make my second term 1 liter over 1,000 milliliters, okay, now I can go ahead and just simply introduce molarity. And I'm not going to flip it because I want liters to cancel. So if I just plug in there the 0.108 moles of H2SO4 per 1 liter of solution, notice things that have canceled. Milliliters cancel, liters of solution cancel, and left with moles of H2SO4, which is exactly where I want to be. 3 sig figs, and you're looking at 0.00378 moles of H2SO4. So now I want to go from moles of H2SO4 to moles of NaOH using the stoichiometric ratio. And so I'm going to recognize that 1 mole of H2SO4 will react with 2 moles of NaOH. So I kind of, I start from the end of the last problem, 0.00378 moles of H2SO4. I want moles of H2SO4 to cancel, be left with moles of NaOH. So it looks like this, 2 moles of NaOH over 1 mole of H2SO4. And then there's no uncertainty brought by the 1 or the 2. So you're looking at 3 sig figs, so 0.00756 moles of NaOH. So there's definitely 3 parts to this. This is the second of 3 parts to work this problem. So now I have moles of NaOH, and I can use molarity to get to volume. So in the last problem, the last part of working this, that's going to be my first term. So if I put 0.00756 moles over 1, now in this case I do need to flip this, don't I? Because I need moles to cancel. So if I take the molarity and I flip it, I have 1 liter of solution over 0.235 moles of NaOH. And sometimes I'll want volume in milliliters and not liters. So I can't remember if I tacked on 1 more term or not. Yeah, it looks like I did. But this would be a problem where, like, I didn't say volume in milliliters, so you could have stopped with that second term. But going all the way to milliliters, if we introduce the factor 1,000 milliliters over 1 liter of solution, round to 3 sig figs, so you're looking at 32.2 milliliters of solution. Any questions? Are you not writing anything down?
I was in the previous ones. I'm just looking at this one. And then...
Okay, that's fine. I was just curious. Okay, so let's do another one. All right, so I think I'll erase this.
For some of these problems, I'd like to go back and see if I can.
Oh, gotcha. That makes sense.
Just by doing it by my own.
Okay. Yeah, I mean, you've been doing well, so that sounds really good. Okay. So the balanced equation for this reaction, it's another acid-base reaction. Actually, it's the same reaction, isn't it? Huh, why did I erase it? Well, we know a few different things about this. So 1 mole of H2SO4 will react with 2 moles of NaOH to form 1 mole of Na2SO4 and 2 moles of water. Okay. So I find the H2SO4 and it says, what is the concentration? So I might go ahead and say question mark molarity. That's what we're after. And it says if 25.0 milliliters of the solution, and that 25.0 milliliters is talking about the H2SO4. So I have 25.0 milliliters of this requires, and now it gives me the volume and the molarity of my NaOH. So I'll say, we'll put my molarity, 0.444 molar NaOH and 27.7 milliliters of NaOH. So this just, only thing that's happened now is we know more about my NaOH. I can definitely use the molarity and the volume to get the moles of NaOH. And then I can use stoichiometry to get to moles of H2SO4. And once I have moles of H2SO4, then I can use volume that I have to get to molarity. So it's just kind of a different sort of, we're after something different, but it has a kind of similar cake to it. So again, the first step is going to be to use molarity and volume of the base, the NaOH, to get to moles of NaOH. Use stoichiometry to get to from the moles of NaOH to moles of H2SO4. And then use the moles and the volume to get to molarity. So here we go. So what do you think? How can I use, what would be my first term and kind of what we've been talking about to get to moles of NaOH from here?
To get to the moles of NaOH. We put the 27.7 milliliters over there.
I would, very good. And then how can I get from milliliters to liters?
And then you take that, multiply by it, and get over 1,000. You
got it, perfect. And then how can I use molarity to get to moles then?
And then multiply that by 1 mole over 1 liter.
Yeah. Well, no. We're on the right track though. It's not 1 mole, it's
0.444.
Yeah, 0.444 moles over 1 liter. Perfect. 3 sig figs, and what you get should be 0.0123 moles, kind of a catchy number, of NaOH. So now we need to use stoichiometry. So to get to moles of H2SO4, so my first term is going to be that 0.0123 moles of NaOH. So what does the ratio look like? To get to from moles of NaOH to moles of H2SO4.
It'd be multiply 1 mole of H2SO4 over 2 moles of NaOH.
Perfect. 3 sig figs, so half of 0.123, you're going to get half of 0.0123, you'll get 0.00615 moles of H2SO4. Very good. Now this last one, actually, to knock it out, I'm going to take those moles, and you're going to see on the next slide, hi Cole, you're going to see on the next slide, all I'm going to do is take those moles and divide it by that volume, because molarity is a ratio of moles to volume, but I'm going to have to fix the milliliters. So it looks like this. So we have kind of come to the conclusion that we must have 0.00615 moles of H2SO4 swimming around in our 25.0 milliliters. But how can I switch, instead of milliliters in the denominator, get liters in the denominator?
You can take you multiply by 1,000 milliliters over 1 liter.
I would. What page are we on, RJ?
We're on page 3 of part 4.
Page 3, part 4. So 3 sig figs, so you're looking at a molarity of 0.246. And what I usually do is, at this point in the problem, I probably would just say 0.246 molar H2SO4. So this sort of problem is a practical problem. In this case, we came up with the molarity of one of our reactants, which is can be very beneficial. I just have to take my word for it. And the problem before this, we came up with volume. So that can also be a very practical thing in knowing how your chemical reaction is going, as to what volume you need to add in order to get to what we call the endpoint. I think what we're going to do on Wednesday is we're going to switch it up a little bit, and I've got a lab I can pull out where you guys will do what this is called a titration, where you take an acid and a base and you basically add one to the other until you use up the one. We'll have to talk to you about acid-base titration. So let's do another one. And it looks like I'm not going to erase it this time because we have the same chemical reaction. But what we know is actually, I shouldn't have erased it. Like, oh great, I'll add it back up again. So we said, or what we did a little bit ago, 25.0 milliliters of the H2SO4. We had both the molarity and the volume of the NaOH. And now we actually, the question at hand is, what is the concentration of the sodium sulfate? So question mark molarity of sodium sulfate. And so actually, what we can do, and I'm not going to reinvent the wheel, we already have, or you have in your notes, the moles of NaOH already. Oops. And we can use stoichiometry then to get to moles of Na2SO4. And then we can actually use, moles. And then we just need to divide by the solution volume to get to molarity. Because once we have moles, all we gotta do is divide by, like I said, the solution volume. The catch here, I'll go ahead and tell you, is the solution volume is 25.0 milliliters plus 27.7 milliliters. So that's the only catch here. So here we go. So earlier when we did the problem, we came up with 0.0123 moles of NaOH. So now to get to, I'm going to pick on you, Cole. So now I want to get from moles of NaOH to moles of H2SO4, and I'm going to use the stoichiometry, this stoichiometry here, that we have 2 moles of NaOH will react and form 1 mole of H2SO4. So we can introduce a ratio. What would that look like from the stoichiometry to get from moles of NaOH to moles of Na2SO4?
Moles of that per 1 mole of Na2SO4?
It would. And so, but what needs to go on the top, what goes on the bottom? You're right.
Mm-hmm.
But do the 2 moles of NaOH, do they go on the top or the bottom? Because I want these to cancel. I'll put this over 1.
Oh, okay. Yeah, the 2 would go on the top, then to cancel on the first one, and then.
So this is over 1.
Yeah.
Yeah. So I want moles of Na2SO4 to cancel. Or sorry, I said that wrong. I'm sorry. I don't want moles. I want moles of NaOH to cancel. So do I put moles of NaOH on the top or the bottom?
Bottom.
Yeah. I think we were saying the same thing.
Yeah, it just,
yeah.
I didn't word it very well.
Yeah, I think we're good with that. So yep, from stoichiometry, I put 1 mole of Na2SO4 on the top, 2 moles of NaOH in the bottom.
Did the 0.0123 come from like a previous one?
Yes.
Oh.
Yep, it came from a previous slide. Yep, we got that from actually just using the what was given in the original problem, 0.444 molar NaOH and 27.7 milliliters of that solution to get to that number. Yep. All right, so no uncertainty introduced by the stoichiometric coefficient. So you're looking at 0.00615 moles of Na2SO4, which sounds kind of familiar. So, is it RJ? Okay, good. Sorry. Ugh. So, RJ, based upon kind of what I said, what our strategy would be, what do you think we're going to do last to finish up this problem?
And then we're going to take that and
Yep, just take this and divide it by the volume. Make sure we know that the volume is both of these liquids. Very good. So if we add the 25.0 milliliters plus the 27.7 milliliters, and don't forget, in this class you need to show all your work, so somewhere you need to show this. Bless you. You wouldn't have to show it as a separate step, but you have to show it. 52.7 milliliters is what's going to go in the denominator here. So if we take the moles that we found, 0.00615 moles of Na2SO4, divided by the 52.7 milliliters of solution. So now, Cole, how can we, molarity is not moles per milliliter, molarity is moles per liter. So how can I go ahead and introduce one more term to get milliliters to cancel and be left with liters in the bottom? So I'm going to do one quick and dirty ratio, and I want milliliters to cancel and be left with liters in the bottom.
So we have 1 mole at the bottom, right, for Na2SO4.
So it's not going to be moles. I want to have, I'll put it this way, I want to have liters down here because molarity is moles per liter. So I want to have liters down here, and I want milliliters to cancel. So what numbers?
1,000 milliliters and 1 liter.
Yep, that was what I was after. Yep. So if I introduce 1,000 milliliters over 1 liter, then my milliliters cancel. That's perfect. And I do have moles per liter, which is also perfect. Remember, this is an exact relationship, so we don't round according to the 1,000 to 1, but round according to 3 sig figs. So on your calculator, you should get 0.117, and again, this is probably how I would finish this problem. I would just put 0.117 m molar Na2SO4. Good. Can't remember. I think I have one more problem. It's a classic. You guys have a lab tomorrow. Tomorrow we're doing a copper lab, so make sure that shorts are okay, but make sure that you don't wear like sandals or whatever. All sorts of little chemical reactions going on tomorrow. So I'm not going to rewrite this on, because it's just too wordy. But even for a chemical equation. But let's just kind of look at what we have. We have 3 reactants. Okay, and it's kind of wrapped around. So we have actually 1, 2, 3, 4 products. It's balanced. Somebody went ahead and balanced it for you. The H2C2O4, that's oxalic acid. The KMNO4, that's potassium permanganate. Of course, the H2SO4 is sulfuric acid. So it says that we have 0.2585 grams of oxalic acid. So actually underneath the H2C2O4, I'm going to go ahead and put that mass. So 0.2585 grams of my oxalic acid. Then it says requires 22.35 milliliters of a potassium permanganate solution. So I'm going to find my potassium permanganate, and I'm going to have to just sort of draw an arrow there. That KMNO4, it says my volume is 22.35 milliliters, and it wants to know what is the molarity of the KMNO4. So I'll put molarity is equal to question mark. Now, the similarity that it may not look like it, but this is similar to what we've been doing. I've been telling you, you look at what you know the most about, and you start from there, and you kind of loop around to the other thing. Well, in this case, what we know most about is the oxalic acid. Granted, it's not a solution at all, but we know we can go from those grams that were given to moles. Goodness. Moles of H2C2O4 using the molar mass. I'll just put mm. So we can use molar mass to go from grams to moles. We've been doing it. And then it's just kind of like the other problems. We can go from moles of H2C2O4 to moles of KMNO4 using stoichiometry, and then we can go from moles of KMNO4 to, moles of KMNO4 to molarity using the volume. It's a little messy, but there we go. So again, we still kind of have three sort of little problems to work. So we need to do a little side calculation, knock out the molar mass of H2C2O4. So we take 2 times 1.008 plus 2 times 12.01 plus 4 times 16.00. We're looking at a molar mass of 90.04 grams per mole. So we said that we're going to use that mass of oxalic acid to get to moles of oxalic acid. So there's our mass, 0.2585 grams of H2C2O4. So RJ, what would be the next term then to get from grams to moles?
And we'll multiply that by 1 mole over 90.04.
You got it. If we go ahead and take our 90.04 grams per mole and we write it 1 mole over 90.04 grams, our grams of oxalic acid will cancel. We're left with moles. That's great. So Cole, how many significant figures to round it to?
4.
4. Yep. Was not a trick question. So 4 sig figs looks like this: 0.002871 moles of H2C2O4. So RJ, what's the next step?
So we want to go to the moles of KMNO4 needed.
Perfect. So if I put this as my, what's the stoichiometric ratio we're going to use?
So there is 2 moles of KMNO4 for every 5 moles of H2C2O4.
Yep. And so we're gonna, perfect. So since we want moles of H2C2O4 to cancel, that's what's gonna go in the bottom. In the top, we're gonna have our 2 moles of KMNO4. Great. Around to 4 sig figs, you're looking at 0.001148 moles of KMNO4. So now we know the moles of KMNO4 and the volume was given. So Cole, how can we get to molarity now? So we know moles and the volume was like that 22 point, or something like that. So molarity is moles per volume.
Remember it.
I'll ask you a follow-up question. So, do you buy this? Since we just did the work and came up with the moles, and the volume was given. So the volume of KMNO4 was that 22.35 milliliters. So can you tell me how can we get it? This is molarity is moles per liter, and this is moles per milliliter. So kind of like we did before, what can I introduce one more ratio to get instead of milliliters in the denominator?
1,000 milliliters over a liter.
Yep, 1,000 milliliters or 1 liter. That's perfect.
Can you go back to that slide though real quick?
Well,
Okay.
cool. So yeah, if we just take the moles we got, 0.001148 moles of KMNO4 divided by 22.35 milliliters of solution times 1,000 milliliters of solution over 1 liter of solution. RJ, how many sig figs?
So,
Mhm.
milliliters, would that count for sick leaves? Because,
Mhm.
or
It's exact, yeah.
it's an exact amount, okay,
Mhm.
then, it would be 4, so.
Yep, he's going with 4. Me too. Yep, very good. So the number rounded to 4 sig figs, you're looking at 0.05138. 0.05138. And then units of that, you can either say moles of KMNO4 for 1 liter of solution, or you could just say 0.05138 molar, the big N. I'll warn you, and we're not going to get to it in this class, but for future reference, there is a little m called molality. So this is actually case sensitive. So I don't know why they did that, but if your m starts to look little, it could mean something else. So capital M for molarity. I don't know why people in science did a lot of things they did. It's like, really? So, well, great. So these will be due on Wednesday. We only have one more part in this unit, so. And then, yeah, so lab tomorrow, and then a week from tomorrow is your test.
We're not going over chapter 5 at all.
So unit 5, we're going to do unit 5, but there will be no unit 5 exam.
Okay. Will it be, sorry, go ahead.
I was just asking if it was going to be the unit exam or the final day at unit.
Yeah, your unit 4 exam. So.
Will any of the things that we over in unit 5 be the same?
A little bit on the in your final exam. Yes. Yeah, your final is comprehensive, so you have just a smidge of unit 5.
Okay.
But most of it's unit 1 through 4. Cool. So I can't remember, is Gabe here tomorrow? No. Okay, for lab.
I don't know.
That's okay.